lost a lot of people there, but that's all right. My name is Marty Swartz. I'm with Max Analytical, which is now part of Thermo Fisher. And our group focuses on developing technologies to go lower and or to remove interferences. So we spend most of our time saying, okay, can this technology do this measurement? And then, if you have the sensitivity to make the measurement, you have all the right conditions to actually do that measurement. And some of the data I'm going to show, you'll see is beyond the extreme. I realize everybody just saw these satellite presentations, but we're actually taking it even a step further than that. So what we're going to talk about is our technology and then how we use it in the field for certain applications. And feel free to ask as we go along. This is our instrument here. This is our Max IR system. It is the most sensitive FTIR ever built by far. We can measure down into the nano absorbance unit range. So if you've never done infrared, nobody ever talks about nano absorbance units. It's a rack mounted system. It's designed to run for 10 years with no maintenance. So imagine if you have an analytical instrument that you never have to maintain, ever. It's actually designed to run 20 years, literally with no maintenance. In the DTGS version that we have here, that's our least sensitive system, and we still are doing single-digit ppb. So for our real sensitive system, which I'm going to talk about, we're getting down to single-digit parts per trillion. All right. The advantage of the DTGS solution, however, gives us the whole infrared spectrum, which means we can measure everything. And as you're going to see, one of the neat things that we can do today with our hardware and our software is we can measure for all HAPs simultaneously in real time with no separation. Now, to do that, we have to add an additional technology, and we call it TOM, because it's basically a thermal oxidizer module. And what it allows us to do is it allows us to create a spectrum in the field that is such a perfect match that we can measure almost anything as long as we have a signal to noise. So what do I mean by a perfect match? So let's say this is my spectrum and this is water, and I'm trying to measure something under that. How well can I match that? Well, if I go to my library spectrum on my computer, the best I can match that is about 1%. So if this is 1 unit high, the best I can measure that is about 0.01. Well, what if I could measure that right before I need it? Can I measure 1,000 times lower? Can I measure 10,000 times lower? Can I measure 1,000,000 times lower? If you have the signal to noise, you can't. This is just our gas cell that we've designed. The nice thing about it is there's no alignment to it. Our FTIR uses zinc selenide optics, so there's no purge required. It's a single, again, some of this is fairly technical to FTIR. It uses a single crystal beam splitter, which is exceedingly novel, because when you're dealing in infrared, heat is a problem. Well, if you have a beam splitter that's 2 crystals sitting next to one another, as the temperature changes, they change. By using a single crystal, you don't have that issue. The spectrometer is rated for 20 years. The gas cell requires no alignment, so if you have to clean it, you just pop it right back in and it's ready to go. All of our systems come factory calibrated for whatever gases you want. And, oh, by the way, it's the same for every instrument. And we can analyze for, say, 100 compounds simultaneously in real time. So this is the TOM, and it's interesting how this came about. There's a lady who asked a question in the last session about methane coming off of engines, compressor engines. Well, methane comes off of compressor engines because methane is a terrible gas for a compressor engine. I mean, reciprocating engines were never designed for methane, right? Turbines were, but not reciprocating engines. You could have thousands of ppm of methane slip all the time. Well, as it turned out, this whole thing came out about because of that. I happen to have a catalyst core that they use for those engines. And we were trying to see if we could find a way to generate a spectrum without the sample. So the whole concept here is, if we take the sample stream, run it through, and you can see it goes around and back. There are actually 2 cores there. We heat those cores up. If we're looking for, say, ethylene oxide, which everybody's interested in right now, as it turns out, you don't even need to heat it. Ethylene oxide through oxidative catalyst core almost reduces completely without any heat. But let's say you want to do BTEX or something like that. Well, then you got to go a little bit hotter. Well, these catalyst cores can go very hot, but this system's only designed for 300 C. What this allows us to do now is get rid of the compound of interest and measure everything else. Again, if I have this spectrum I'm trying to get rid of and I'm trying to measure something down here, I need an exact match. So then when it's running in sample mode, or what we call bypass mode, it just goes in and out. So the software is set up so that the system can collect that spectrum through that oxidizer anytime it needs. So if I'm doing ppb level stuff, maybe once a day. If I'm doing ppt level stuff, maybe once an hour. It just depends on how low I want to go. So for those of you that are not familiar with infrared, this is what the infrared spectrum of air looks like. And this is at 50 atmosphere meters. What that means is if I had a beam of light going through the air, it's 50 meters long. In this case, I just pressurized it into a 10-meter cell. So I had 5 atmospheres in a 10-meter cell. So all of this here is water. This is CO2. This is all water, and this is CO2. So we're going to measure in this area here. So ethylene oxide absorbed right here. BTEX absorbs right here. Things like CO and NOx are over here. And then all the hydrocarbons, if they have any kind of functionality, like ethanol or anything like that, are going to be over here. Okay, so as you can see, you may not be able to see the units, but that first scale is 0.2 absorbance units. 0.2 is a very big peak. 0.3 means you have 50% of the light is absorbed. Okay, so 0.2 is a fairly big peak. These are about 0.1. And the peak we're trying to measure is 100,000 times smaller. Okay? So I'm going to show you some results first, and then I'll show you how we did it. So what we did is we just told our software to measure all these compounds plus another list, but it was too crowded to put all of them on there. These are all being measured simultaneously over a 90-minute period. And I call this an up-down plot, if you will. So this point here is the highest point that it read. This is the lowest point that it read over that 90 minutes. So if it was evenly distributed around 0, you have no bias, and the average is 0. So most of the points are like that. Some are taller, some are shorter. If you look at things like phosgene over here, only like 1 ppb. This is, by the way, the scale is 20 ppb. So it's just showing that most of these are not there. So we were doing our own lab. We have hundreds of compounds in our lab. We just happened to want to see if any of them were actually in the air. Well, as it turned out, we actually picked up a couple. We picked up IPA. We picked up formaldehyde. There was probably a little bit of ethanol there. If you notice, all the points are positive. It said there might have been a little bit of aniline, but it's a very weak absorber. We certainly have acetaldehyde in our lab, and it showed up as being positive. All right, the point is, all of these compounds are being measured simultaneously, no separation, once every 30 seconds. So this is what the data will look like if you happen to have one of our systems. All the compounds are listed here. Their instantaneous value, a few seconds, is here. And as you can see, most of these are below 10 ppb. Most of the standard deviations are below 3 or 4 ppb. Many of them are less than 1. So the sample spectrum that we were just talking about is there. And then this one, I'm not going to hit the button just yet. This is the concentration plot over that time. So if you see where it's at 0 right here, that's when we're running it through the top. We're saying, okay, collect the 0 spectrum and then immediately switch to ambient air. And as you can see, it goes up immediately. And then it starts to decay. It drops back down to 0 here because we told it to go through the oxidizer again just to make sure it was 0. And it went back up. And just in case you can't see it, that's about 145 ppb. For those of you that are not, again, FTIR people, IPA is a very weak infrared absorber, and we can easily see that. A couple other things. That's the concentration plot. This is an R-squared plot showing you that, in fact, wherever we're not zeroing it, we're getting an R-squared of about 0.97, 0.98 through all the measurements, which is saying, okay, it's IPA. This is what we call a single reconstruction plot. And what this is that sample up there minus everything except IPA. So the red is the IPA spectrum in our library. The black is the sample. And that's the match. So it's clearly IPA. And then the thing above it is what we call a residual. It's the red minus the black. And the ideal residual is basically just noise. And of course, we're doing that for all the compounds. This one just happened to be the largest. Okay. So now what I'm going to show you is what it looks like if I didn't do that. So if I were just using a standard FTIR, going to my reference library, pulling the water out, and then using that. So this is what it looks like with it. This is what it looks like without it. So this red peak here is the same height as this red one. Okay. So this scale is 10 times bigger, meaning the noise is 10 times bigger. The R-squared now is 0.05. This is exactly the same data mine. And as it turned out, the software actually got it right. This is the prediction. And it actually got the analysis right, but you'd never say that as IPA. It doesn't look anything like IPA. And so that's the difference between using reference spectra and using spectra that are actually generated in the field or on a process in real time, especially if you've got interferences like water, and water is the biggest one. Just to show you what the sensitivities are, again, this is a shorter list, all the MDLs versus the OSHA PELs if this were a ambient air monitoring system. All of the data is at least 30 times the PEL. Even for something as toxic as phosgene, the detection limit was 2 ppb, and the PEL is 100 ppb. So we're 50 times below that, or above that. I mean, below that. I mean, 50 times better. Okay. Okay. So now we want to go to the extreme. That was the easy stuff. Okay. So now we want to try and measure even lower, which means we want to measure that water even better. And we were just playing around one day. I have to thank Montrose for this. It wasn't their idea, but they lent me the device. What I wanted to do was I wanted to run the sample through a chiller, get rid of the water, and make sure I could still measure the compound, which I could. As it turns out, ethylene oxide does not come out in the chiller. I could demonstrate that by spiking it in, it didn't come out. But it gave us an idea. Everybody's seen compressors, right? And the one thing you know about compressors, if you compress ambient air, they drop out moisture. So what we did was take the tube from the compressor, or from the chiller, took it out of the chiller, and we put a little piston pump like this, so that as the air was coming out of this vehicle, we were doing a vehicle test, but it was ambient air too. And all we're doing is we're pressurizing this chamber to 10 atmospheres. So let's say, for instance, the moisture in the air were 3%, the most it could be. If I take air at 3% moisture, pressurize it to 10 atmospheres, I only have the equivalent of 3% water in that. So then if I were to release the pressure, I end up with 0.3% moisture. And that's lower than the chiller can get. So I'm not using a chiller, all I'm using is a compression tube. And I can get lower moisture. And I'm not cooling it, so I don't have to worry about losing compounds. So what we're going to do is we're going to pressurize this tube, and then right at the exhaust of that, we're going to set it to another pressure. It could be 1 atmosphere. And if we don't have a lot of water interference, maybe we'll leave it at 5 atmospheres, because now we have more gas in the gas cell. And then from there, run it to the IR. But the advantage of this is it reduces the moisture, and now it's a constant. Imagine if I had an instrument measuring 20 locations in the Gulf region outside, some near steam generators, some not. The moisture levels are going to be all different. Here, I get the moisture every time at lower level than a chiller could get. And I don't need peristaltic pumps or anything. I just have a chiller with a little vent on the bottom. I mean, just a tube. So as I just said, no chiller, no consumables. We can actually reduce the moisture lower than what a chiller can do by a lot. And it minimizes the variance in the moisture concentration. So what you see here is that that's the TOM up on top, that's the max IR, and then that's our little effective chiller. So just to make sure it works, we injected 200 ppb benzene. And what you see here on the time plot is 0, then it goes up to 200, back to 0. But we didn't change the concentration of the benzene. It's 200 ppb all the way along. Where it's going to 0, it's going through the top, just to demonstrate that we're removing it all. So yeah, we can get 200 ppb through the chiller, and B, we're removing all the benzene when it goes to the TOM, so that we have a spectrum that is free of benzene, because we're going to use that to do our analysis. And as you can see, it works very nicely. And then this was the same data set, or a similar data set, just looking for more compounds. So what you see here is just time data. This is about 20 ppb, that's about minus 20. I think this was at 5 atmospheres. All right, so these are basically at 0 for this particular measurement. As you can see, where they start to come together, that's where we ran it through the TOM. So the formaldehyde actually came down as well and then went back up. So the only compound that was in this air basically was the formaldehyde, and it was around 75 ppb. So it's just showing that by using this, we can now measure pretty much anything in the infrared spectrum that we want at pretty low levels. Okay, now for the really hard stuff. Okay, ethylene oxide is of interest for many reasons right now because of its toxicity. And the EPA came to us and said, okay, we want to measure ethylene oxide, not at 100 ppm. We want to measure it at 10 ppt. Okay, only 10 million times lower than that. Okay, so my peak, my ethylene oxide peak is like this at high resolution. This is the spectrum of ethylene oxide at half wave number. I need to measure 10 million times lower than that peak. So A, I gotta have the sensitivity to do it, and B, I better not have any interferences because I'm never gonna be able to make that measure. And then, oh, by the way, I got another problem. FTIR instruments, they're infrared instruments, which means they're temperature sensitive. Well, if you were to take this spectrum over time, just continuously, the baseline can move this much, 0.1 absorbance units. It's common for that to happen. Well, if that peak is 0.6 and my baseline can move 0.1, and I'm trying to measure 10 million times smaller, it's not possible. Just can't make that measurement. So what do? First thing we do is we use a thing called auto-rep. And again, this is getting a little technical for the FTIR part, but what we can do with infrared, in FTIR specifically, when you collect a 2-wave number interferogram, that 2-wave number interferogram has half of that would be 4-wave number, half of that would be 8-wave number. So what we're going to do is we're going to just take that single spectrum, that single interferogram, process it at 2-wave number, an 8-wave number, and then the 8-wave number becomes the background. This way you have 0 baseline drift. If you notice, look at the baseline, it's right at 0. Even where this broader features are, they're all at 0. So now we have a way to keep 0, 0. Okay? Now the peak got a little bit smaller because we're losing resolution, but we gained a lot in signal to noise, and we got a lot in baseline stability. So does it work? Okay, so this is a real life instrument in the field. It's a 20-channel system. There's your sample spectrum up on top. Where the red is, that's your ethylene oxide peak. That straight line, that's the peak, okay? Here's the concentration plot. The scale is 1,000 ppb. This is actually real data. This is actually ambient air data at a sterilizing facility. I won't say which one. because it's obviously way too high. 1,000 ppb is just not supposed to be there. So a couple interesting things. You see all these points here that go up and down as it's going through the different channels, but notice how the R squared value is the same. It's saying, hey, I have no interferences. I got it right. The only time it drops down to 0, these were probably 0 steps. We were running the TOM and it was running through 0. So the point here where the green line is 12 ppb. Here's our single reconstruction. Again, the red is the calibration spectrum, the black is the sample, an exact match, minus the noise, and then a perfect residual. Okay, fine, that works. But they don't want 12 ppb, they want 10 ppt. So we only need to go 1,000 times smaller. Okay? I wouldn't be here if I couldn't tell you how to do it. Okay, so this is a really nice peak, but for those of you that know anything about infrared or anything about spectroscopy, this peak is 1 times 10 to the minus 4 absorptions. Okay? That's 0.1 milliabsorptions. And we got to go 1,000 times smaller. That means we've got to measure 100 nano absorbance units. If you ever used a UV vis in the lab, it went 0.001. We're trying to add 4 more zeros before that 1. Not easy. Just before that, we did a study. This is a 3-month study, just showing the stability of the system. In their case, this is 1/20th of their drip limit that they were, or their emission limit. This is actually an emission system. So they could go up to 200 ppb. And then the different dots there, the X's are when the TOM was running, just showing you that they're basically around 0. And the diamonds are when we were running nitrogen, showing that there is no drift between the two. That's an excellent way of showing that interferent is not biasing the data. Now, in this case, this is our first generation system. This is a couple years ago, and it was 3 ppb MDL. Okay. I want to show you what it actually looks like. So here's our ethylene oxide peak. That's 150 ppb at 50 atmosphere meters. Here's what water looks like overlapping it. And if we want to get down to 10 ppt, we need a peak that's 100,000 times smaller than that. Just to put that into perspective, what that's saying is we're trying to measure the thickness of 2 contact lenses under the Empire State Building. Okay, and not just measure that they're there, but measure their thickness. Okay, that's how big that peak is to what that one's going to look like in 10 parts per trillion. Okay, so the very first experiment that we did, we used our TOM, we used our little knockout device to stabilize the moisture, and this was done in our lab. And we got to about 170 ppt, which we kind of expected some ethylene oxide in our lab because we have cylinders of it. And okay, it looks like it. But the EPA wasn't even close to satisfied. They were like, okay, great, but we want to go 10 times lower, 20 times lower. The residual up there at the top is plus or minus 1 microabsorbance. Remember, I said we're trying to get down to 0.1 microabsorbance. So, I just threw this slide in because in one of the previous talks, they were talking about how the ambient air ethylene oxide in the world or in the US is around 200 ppb or 200 ppt. We don't believe that's the case. We think it's actually much lower than that. So what this is, I would never normally put this in, but it was the only data I had. What we were doing is we were just going TOM, spike in 200 parts per trillion, TOM, and this is real-time data. These are only like 8-second measurements. 200 ppt. So if I were to show this in a normal setting, I would zero the 0 point because I know this is 0. I know this is 0. But the point is, we're getting about 200 ppt injections. You can see that. Right? Is it perfect data? No, it was actually the first time we even tried it. But we wanted to show that we could get that through the TOM, through the compression system, and not lose it. Okay? And again, when you get down to this level, you're not going to be reporting at 8-second intervals anyway. You're going to average. So that's what we did. So this was ambient air, and because water is our biggest problem, we did it during a rainstorm outside. And so what this is, these are basically 3.5 second averages, so that we zeroed and then we measured 7 times over the course of an hour. And so the scale here is 0 to 80 parts per trillion, and the average is 30 parts per trillion, with the standard deviation of 26 parts per trillion. Again, 8-second measurements, but average is 3.5 minutes. Those red dots are the variants of the methane. We want to monitor that. So I just put those on. That's what's on the other scale. There's slight changes in the methane level. So again, we're not down to 10 ppt, but that's saying that we're below 1 microabsorption. All right. And the other interesting thing is all the data are positive, which suggests that, okay, maybe there is a little bit of ethylene oxide in the ambient air. Maybe it's in the 20. And as it turns out, we've repeated this experiment a number of times. And every time we do it, we get between 25 and 30 on the average. Yeah, we get some outliers here and there. But again, we're talking about a peak that is infinitesimally small. And yet we get the same statistical average every time we run the experiment. Just a little promo for our company. We build ambient air monitoring systems for things like HAPs and ethylene oxide. It's a fully integrated system. It talks directly to factory interfaces. It can run indoor air, outdoor air. It doesn't matter. And as I just showed, depending on the configuration, we can handle interferences that are even 10,000, 100,000 times bigger than what we're. So, when I first started doing FTIR, nobody was talking parts per trillion. Nobody certainly was talking even microabsorbance unit measurements, much less nanoabsorbance measurements. We now have the capability to do that, but to do it, you need additional accessories to get down to those levels. And I'll stop there. Thank you for your attention. Any questions?
How do you control the